When people think of science fiction or futuristic technology, many different ideas come to mind, but one topic in particular always gets brought up: human-like robots. Whether they're referring to the droids from Star Wars or the titular Iron Giant, robots that can move and behave like people have captured the public imagination for many years. However, this image of robotics was merely a work of fiction. The field of robotics has expanded far beyond human imagination. The work that began in the 20th century has finally borne fruit, with companies unveiling bipedal robots that can walk, run, and even dance. As entertaining as it is to watch robots do a whole dance routine, developing bipedal robots isn't purely for fun and games. By using legs for upright walking, robots are better able to navigate through complicated terrain, allowing them to take the place of humans when performing tasks in dangerous environments, like on roads covered by ice or in malfunctioning nuclear plants littered with spills. That's the end goal, but maintaining stability is hard, and stability on low-friction surfaces is even harder. Maybe a hint can be found here. As one of the few bipedal animals that trek across slippery surfaces consistently, there must be something about penguin anatomy or penguin movement that allows stability, even on ice. The penguin waddle also happens to be extremely energy efficient, so taking inspiration from it wouldn't be a bad idea at all. This is the current iteration of the bipedal robot based on the penguin waddle. As you can see, it could use some adjustments to help improve its stability. But the question is, what hardware changes need to be made? Different species of penguins have different anatomies and different biomechanics, so how would changing a robot based on different penguins affect its gait? In order to better examine the penguin waddle, inverse kinematics is required. Inverse kinematics uses the movements of the object of study, the penguin's body parts in this case, and calculates the joint's position and range of motion throughout the whole movement. In this research project, the two requirements for inverse kinematics are penguin movement data and penguin models to map the data onto. The first requirement can be met by seeing penguins in action. Here we see one of many videos of penguins walking on a treadmill. By running each of these videos through a program, the different parts of the body, like the head, flippers, and feet, can be tracked and imported onto a model. I automated the filtering and brightening of the videos to allow for better tracking of the different movements. The second requirement for inverse kinematics, the model, is met by these 3D models of a Gentoo penguin and a king penguin, constructed from CT scans of specimens provided to us by the Obihiro University penguin team. As they are, the models are just stationary, and we need to see the models move to properly analyze the biomechanics of penguin locomotion. That means the individual 3D coordinate systems need to be added to all the joints to represent points where the penguin can move, as I've done here. And then, with a bit of coding magic, the model can be converted into a format that can be uploaded onto OpenSim, a biomechanical analysis program. Here, we can see that the points where the coordinate systems were added are where the skeleton can be moved and rotated. Once the penguin movement dataset is completed, the skeleton will be able to show the exact poses of a penguin in motion, which is exactly what we need for inverse kinematics calculations. A lot of work has been done just to set up these inverse kinematics calculations, but the results are something to look forward to. Finding the differences in the biomechanics of different penguin species and deciding the optimal changes to make will be an interesting process. There's also the center of mass to consider, which can be calculated using the mass of the penguin model's parts and their location. The center of mass is integral to balancing for all things in the physical world, so hardware changes that affect it will have to be done carefully. There's still a lot of progress to be made, but two things are for certain. This little robot will be seeing a lot of change, and the stability principles that are uncovered from these changes will be applicable to other humanoid robots, further expanding the areas in which they can be employed.